Welcome to Module 1, General Networking Theory. In this module, we're going to look at everything from the basic general routing concepts, like what is route summarization and what is split horizon, all the way up to redistribution, a favorite topic for the written as well as the practical lab exam. First generation routing protocols are distance vector routing protocols. They engage in something that we call routing by rumor. Here's what these routing protocols will do, believe it or not. They will periodically, at a timing interval, pass the entire routing table to each other. That's what they're doing. They're just literally saying, okay, here's everything I know about for routes on the network, and they pass this table to their neighbors regardless of how stable or unstable your network is, how many changes there are in the network. This approach is very prone to problems. In fact, it reminds me of a game that we played in elementary school, or maybe it was even pre-elementary school we did it, but it was a great game where we all sat in a circle and the teacher would tell one of the students something, a phrase. Maybe it was like, the sky is blue and it is a nice day. And the person would then tell the person next to them, and they would tell the person next to them. And by the time this phrase got all the way around the circle, it barely resembled its original form. And this is a great analogy for what can happen when we are routing by rumor in the network. Now, the protocol that you want to be concerned with in the written and the practical lab exam, as far as distance vector routing goes, is RIP, the Routing Information Protocol. This is the only pure distance vector routing protocol that we are going to concern ourselves with. A far superior approach to routing is link state routing protocols. We can consider these second generation protocols, and they are much more sophisticated and much less prone to errors. Link state routing protocols use this wonderful concept of hierarchical routing. We're going to use areas with our link state routing protocols. And instead of flooding the routing table, the full routing table, like we saw in distance vector, we are instead just going to flood within only our area updates about our link status. You see, each device in the area will take updates about these links called link state advertisements, and each device will create their own accurate map of the area. So before we had routing by rumor, now we have each device taking these link state advertisements and devising their own map of their particular area. A great example of a link state routing protocol is Open Shortest Path First, or OSPF. One of the most interesting routing protocols that we'll be looking at in detail in this course is EIGRP, the Enhanced Interior Gateway Protocol. You see, Interior Gateway Protocol, its predecessor, was a distance vector routing protocol, and Enhanced Interior Gateway Protocol takes the best of both worlds. It is what we call a hybrid routing protocol, and it possesses the best qualities of distance vector with the best qualities of link state. So this is a truly unique routing protocol in that it does possess some elements of both first generation and second generation technologies. Now you may be wondering, what about the border gateway protocol? We haven't mentioned that one yet. Well, to learn a bit more about the border gateway protocol, click the Note button that has appeared on your screen. Because there is the potential for routing problems, like particularly routing loops with distance vector and even with link state protocols, there are a number of routing problem solutions that have been developed over the generations of our routing protocols. Let's take a look at those now, and there's one in particular that you really want to be aware of for the CCIE written exam. First of all, there's the concept of an invalidation timer. This is the fact that a router will literally want to be updated about a specific piece of information, and if there is no update received about that particular prefix over so many intervals, the route will be marked as unreachable. There's a hop count limit. This eliminates the counting to infinity problem, where specifically RIP routers, for instance, might say, okay, I know how to get there and it's 4 hops, pass it on. I know how to get there, it's 5 hops, pass it on. I know how to get there, it's 6 hops. All the while, the route may be unreachable and they're using stale information. RIP in particular adds a hop count limit, and it's a very famous one. You can't have more than 15 hops in a RIP network. Triggered updates are a great improvement. If there's a change in a particular prefix, the update will go out right away as opposed to waiting for the next update interval. And then there's the concept of hold down timers, which routing protocols can use. If the metric worsens for a particular route, routers can not accept updates for a specific delay period. There's also asynchronous updates. This ensures that all routers don't try and update each other at the very same time. Oftentimes, routers will add some kind of a random delay component so that they don't update at the same time all other routers do. If a route is poisoned, the metric is immediately set to unreachable. And this is a great technique to ensure that all routers get this information and they mark the route as unreachable in their forwarding tables. Now, the most important one for the CCIE written exam is split horizon. Split horizon says, okay, in order to avoid bad routing information and potential routing loops, do not send an update out an interface where the update was learned from. This makes great sense and typically is a great step in avoiding routing loops. So once again, with split horizon, we are not going to send an update out an interface where we learned the update. It's kind of good common sense when you think about it. And split horizon is indeed a loop prevention mechanism. Now there is one exception to split horizon that I want you to be aware of. The creators of these protocols said, you know what, it's a real good idea for us to add an exception to split horizon, and that exception will be a poison reverse. We want to make sure that poisoned routes are disseminated everywhere, so that is an important exception to the split horizon rule. Being able to send an update out an interface where the update was learned, but only if that update is a poison reverse update. Where frame relay can immediately get us into trouble in, for instance, the CCIE lab exam, is when we have frame relay hub and spoke topology. You see, what's going to happen here is split horizon can cause us a real problem. When the spoke router R5 sends an update to R3, notice that it's going to go into the serial 1/0 interface. R3, due to split horizon, is not going to want to send the update back out that same interface. Now it's interesting. The open shortest path first protocol, we are not going to have a split horizon concern. With RIP and EIGRP we would, but the great news is RIP, believe it or not, is smart enough to automatically circumvent the split horizon problem. So with RIP, we will not have a problem with split horizon. So the one protocol that's left for us when it comes to our CCIE lab exam is EIGRP, and we are going to have to go in and turn off split horizon in this scenario if we want updates from R5 to enter serial 1/0 and propagate to R4. Obviously, it would be the same thing with R4 updates entering that interface and being propagated to R5. Summarization, also known as prefix aggregation, is a great technique used in modern networks in order to conserve router resources, reduce the size of our convergence domains, improve manageability, and simplify redistribution. When we say reduce the size of convergence domains, what we're referring to is literally there being kind of a change in the network and routers not having to update a lot of other routers about that change. Summarization literally ends up kind of hiding these network instabilities from the rest of the network, and this is a wonderful thing. With a lot of routing protocols, when we create a aggregate or summarized route, we'll see that a static route to null 0 is created. Very important for you to realize that this static route to null 0 is a loop prevention mechanism. So the idea here is when we're summarizing, we might not have access, our router that's summarizing, to all of the address space in the summary. So to guard against us having packets forwarded to us, and then us forwarding them back, and then having them forwarded to us, and then us forwarding them back, is a static route L0 for the summary, so that we will throw packets away where we are summarizing for that space, but we don't have access to that actual space. We'll throw those packets away as opposed to forwarding them and creating a loop. This is the very important role of the static route to null 0 you may find during summarization. Summarization is such a great thing that some protocols want to do it automatically, and we typically don't want this done for us in our topology as a result of problems that it could create. Both RIP, Routing Integration Protocol, and EIGRP for our interior gateway protocols are both going to want to engage in this automatic summarization by default. And again, we typically turn this off with the no auto summary command. We typically don't want the summarization to occur automatically because maybe we have a situation where we have discontiguous subnets. We have some subnets of the address space over in one corner of the topology, some subnets of the address space over in the other corner of the topology, and this automatic summarization will cause a problem, as we'll see later in this presentation. So what we do is we turn off this automatic summarization behavior, and we go into our topology where appropriate, and we create manual summaries of particular portions of the topology. Routing protocols are kind of interesting because this is the one time in the world that classless is a good thing. I was always raised where being classless was a real problem. But with routing protocols, we want our routing protocols to be classless. Here's why. A classless routing protocol will send subnet mask information in its routing updates. Yeah, imagine that. Classful or first generation routing protocols do not send this subnet mask information in their routing updates. Therefore, we better not have discontiguous subnets, as we'll see in a moment, and we better consistently use a subnet mask. The consistency of the subnet mask in your network is assumed when you're using a classful routing protocol, because once again, your classful routing protocol is not sending subnet mask in the updates. When we do send subnet mask information in our updates, in other words, we're using a classless routing protocol, we can now engage in an awesome technique for addressing your internetworks, and that is the variable length subnet mask. Variable length subnet masks allow us to address our network in a very, very efficient manner. The IP classless command is something you should also know about. You're going to find this on your routers by default. And what the IP classless command allows your router to do is when it receives a prefix that's being forwarded to, it will check its prefixes. If it doesn't have that particular subnet, it will go ahead and use the default route. That's exactly what you would want it to do, right? Maybe we have the 10-10-10 subnet in the table, the 10-20-20, and the 10-30-30 subnets. If we get a packet destined for the 10-40-40 subnet, not in our routing table, we want to go ahead and forward using the default. Without the IP classless command, very important for you to know that your router will actually drop that traffic and not use the default route. Now, your device, your router, is going to potentially have a lot of different route information in its table. How does the router decide which of these many routes to use? Well, here's how the decision criteria works. First, the router looks at all of the route protocols that are telling it how to get to a destination, and it measures them against each other using a concept called administrative distance. We're going to look at administrative distance in a lot more detail in the next lesson of this course, but just trust me in that it's a trustworthiness measure that the router is going to use. If, let's say, RIP, EIGRP, and OSPF all indicate they know how to get to a particular prefix, the router is going to use this trustworthiness measure, this administrative distance, and it's going to select the routing protocol with the best measure. Administrative distance is like a golf score. The lower the value, the better. And let's say it's an EIGRP internal route. Of these three different protocols, EIGRP would be selected as the best path to get there due to its highest trustworthiness measure. In this case, the lowest score of 90. By the way, the comparison there would have been 90 versus 110 for OSPF versus 120 for RIP. Once it figures out the best route to install based on administrative distance, then it will look at metric when it's making the decision. Maybe we have a couple of different ways to get to that prefix, all learned by EIGRP. Now it's going to look at the metric for EIGRP, and it's going to compare those paths. And then finally, the one that will win out when everything else is equal, for instance, is prefix length. The longest match is going to win. So it always looks at the subnet mask, and it is going to try and find the best match or the longest prefix match. I have an example here of a routing table. Notice that EIGRP tells us how to get to 10.200/26. RIP tells us how to get to 10.200/24, and OSPF tells us how to get to 10.200/219. Notice that each of these different prefixes was installed in the routing table via a different routing protocol, and that's because they all have varying length prefixes. They're not all routes to the same exact prefix. If they were, administrative distance would have kicked in and silenced some of these routing protocols. But in this case, we have all of them installed because of the different prefix lengths, and if we are going to route traffic to one of these prefixes, the longest match is going to win. Typically, in our example here, that's going to be the EIGRP route due to the /26 mask. Many of the students that are watching this Class on Demand series are here actually not to pass their CCIE written exam. They're here to review and refresh for the core knowledge short answer questions that are presented in the lab exam now. In order to help those students and also to help those studying for the CCIE written, here is a short answer core knowledge exam simulation question. Go ahead and type your answer in, and when you submit your answer, you'll be able to see what we deem as the correct answer on the next slide. So enjoy the core knowledge lab exam sim. Well, congratulations on completing Module 1, Lesson 1 on our general routing concepts. Please join me in the next lesson where we are going to take a look at, in much greater detail, at forwarding database that we call the Routing Information Base or Routing Table.